what's up, everybody? So we're on week 8's notes. You can find them in exam 2 or exam 3 on Blackboard. Today we're going to cover the last little bit of chapter 3, which will be on the exam. After 3.8, everything else won't be on the exam. All 3.8 is about is this idea of a differential. And a differential can be thought of in 2 different ways. It can be thought of as an approximation measurement or as an error measurement. Now, to show all of this, let's think back to how we define the derivative. We said that the limit as delta x goes to 0, f of x plus delta x minus f of x divided by delta x is equal to f prime at x, right? More specifically, it's equal to dy dx, or I should write it like this. Having said that, notice we can make an inference about something. The limit as delta x goes to 0, delta x is equal to dx. So what we're saying is that for really small changes in x, so for really small delta x's, it's going to approximate to dx. Now dx, according to Liz, looks like it ought to be 0. Really what it actually is something very close to 0, but not 0. And this becomes a little bit clearer with other calc courses, but I want to make this point first because when we start talking about dy and dx and the differentials, what we're going to say is that if we multiply both sides by dx, we get dy is equal to f prime of x dx. And this is kind of like multiplying this by dx, right? If we're multiplying both sides by dx, then we should get dx over here. And we're saying that dx and delta x are pretty close together. So let's drop the limit for a second. We're going to say this thing approximates. And I'm going to make a statement here. We're going to find that we can cancel out the dx with the delta x when we multiply both sides. You're going to be left with f of x plus delta x minus f of x, which is equal to delta y. So all we've done here is we've said we're going to let this thing get really small, and it's going to approximate dx. When that happens, we can say these 2 things almost cancel out, so these 2 statements are approximately equal. Does that make sense? So the idea is, let's say we have a number z. Now let's say we divide z by z plus 0.1. Well, that's almost like z over z, right? So this is almost 1. And in that way, we have dx over delta x is almost the same. And that's why we say for small delta x's, this happens. Does that make sense? People at home, is this making sense?
Yep.
Yep, awesome. All right. So because of this, we can take one step, we can go one step further. Say, well, hey, if dy is approximately equal to delta y, and dy is equal to f prime dx, then we can approximate delta y with f prime dx. So we have two different things going on here. The first thing is that dy is equal to f prime of x dx, and delta y is equal to f of x plus delta x minus f of x, and that delta y is approximately equal to fyx dx for small delta x's. Also notice this works in both directions. If we hold dx to be small and we multiply both sides by it, then we still get that same approximate cancellation here, right? Now I point this out because when we use all of this in a second, it'll make more sense what's happening. And their point here is that, again, when delta x is really small, we're going to approximate these same sort of values. Now, as an example of this, let's consider we've got the function x squared. We want to approximate dy and delta y so we're going to say choosing x to be 1 and delta x to be equal to, my mistake, dx, to be equal to 0.01. Really, this should be an approximation because delta x can't be 0.01, but it can be approximately 0.1. All right, now having said all of this, solving for dy, going to be the derivative of our function times dx. Well, the derivative of our function is 2x, right? Saying x is equal to 1, times dx, that's 0.01. So this whole thing's going to come out to be 0.02, right? This is dy. Now delta y is going to be equal to f of x plus delta x minus f of x. Well, this is going to give us 1.01 squared minus 1 squared. What this is going to come out to be now is 0.0201. Yeah. So we can see that for small dx's, for small delta x's too, these two things come out to be approximately equal. Because we have 0.02, 0.0201, right? We're off by what? 1/10,000th? So comparing our answers to the process, we know that the derivative of x squared is 2x. We're given that x is 1. We're told to approximate dx as 0.01. So calculating dy, we get 0.02. Now, calculating the actual change in y, we get 0.0201. So this is an important distinction to make. This is an approximate measure of the change in y. This is the actual measure in the change in y. Right? We said y1 minus y0, right? So this is the actual change, delta y. This is approximating it, saying, well, for small enough dx's, or delta x's, it's about 0.02. And if we were to choose smaller and smaller delta x's, we would get more and more accurate measurements here. Make sense what I mean? So having said that, there's a natural question to ask. Well, when the hell am I going to use this in business? This is, after all, business calc. You can use it for marginal analysis. So recall that marginal revenue is going to be dr dx. Marginal cost is going to be dc dx. Marginal profit is going to be dp dx. In that case, you can approximate changes in your revenue, cost, or profit by using this method. Now, why would you do that? You're already going to be calculating marginal cost, marginal revenue, marginal profit. So why would you go ahead and say, now that I have that measured, let's go through this process. Why would you do that? Instead, you could do this. It's a little bit quicker. Does that make sense? What I mean? So as an example of this, got this demand function. So remember, price is set by demand, and that's what we call our demand function. And revenue is going to be price times the amount of product you sell. So we started off with our demand function, which set the price as a function of demand, right? And then we said, all right, cool, this thing times X is going to give us a revenue function. The derivative of our revenue function is going to give us our marginal revenue. Now, we're going from X1 is equal to 149 to X2 is equal to 150. So delta X is equal to 1. We're going to choose X to be our first X value, the lower of the two. Make sense? We're going to choose X to be 149 here. Now we're going to go through and say dr is equal to r prime of x times dx. This is approximately going to be r prime of x times delta x. So this comes out to be our prime of x evaluated at 149 times 1 should give us 102, I think. All right, 149 times 2 is going to be what, 3? Yeah, it'll give us 2. So it won't, it'll be 298, so it'll be 102. Make sense? So looking at dr, we go through, we say, hey, let delta x, they say be equal to dx. It should actually be approximate. This is 1, then dr is going to come out to be 102. Now, if we compare that to evaluating delta R, which is revenue at 150 minus revenue at 149, that's going to come out to be 101, just like it says down here. So these things approximate each other. They're pretty damn close. And that's the point of this, is this is a good back of the napkin approximation to questions you might actually be asked. In a work setting, you might be asked, right? So having said that, as another example, for those of y'all at home, this is slide 11. This is another example. Imagine we have a profit function, 0.0002x cubed plus 10x. Then the derivative of this thing is going to be 0.0006x squared plus 10. If we want dp, as we move from 50 to 51 units, then setting x equal to 50 and delta x equal to 1, we're going to get that dp is equal to 1150. Now compare that to the profit function calculated at 51 minus the profit function calculated at 50. It's going to come out to be 1153. So again, these are close approximations for each other. Having said that, not every function is created equally insofar as how we're going to find the differential. In general, though, anytime you have a function, and you actually write this out slightly different. So I wanted to write this out slightly differently just so that it becomes a little bit more clear what's happening here. Anytime we take a derivative of the product, this thing's going to come out to be f prime of x or dy dx is equal to, let me, just so I can keep with the notation, use df. This is going to come out to be u of x times dv dx plus v of x times du dx. So moving that differential dx across, we're going to get that df is equal to u x dv plus v of x du, which is how they got the product rule here. And they used a similar logic for the quotient rule, because the quotient rule is going to come out to be dg dx is equal to v of x du dx minus u of x dv dx all over v squared. So when we multiply dx all the way through, we get these cancellations here. And we're left with dg is equal to v of x du minus u of x dv all over v of x squared. So just showing where these formulas come from, right? All we're doing is we're multiplying this dx all the way through up here, or through over here. Having said that, it's not quite that simple. Properly said, we have to unimpose the limit, multiply by the difference, by the change in x, the delta x, and then reimpose the limits. But the details here are for an upper level course. Does all of this make sense to everyone? Folks at home, what do y'all think?
Yeah.
Yeah, cool. Awesome. In that case, just a couple examples of differentials. We've already seen this first example. Looking at the third example, C, y is equal to 2x squared minus 3x. Well, the differential is going to come out to be 4x minus 3 dx. In that last example, we have y is equal to 1 over x. The differential is going to come out to be dy is equal to negative 1 over x squared dx. Now, having said that, a minute ago, like I said, we could think of these as measurements of error. That's what we're about to talk about now. In this problem, what we've got going on is we have this caliper that we're measuring a sphere with. The caliper tells us what the radius of the sphere is. So for those of y'all who aren't familiar, this is what it looks like to measure with an old school caliper. It's telling us that the radius of the sphere is 0.7 inches. Now we know that volume of a sphere is equal to 4 over 3 pi r cubed, right? If that's the case, then the derivative dv dr is equal to 4 pi r squared Now, we've measured the radius to be 0.7, but the caliper is only accurate to the second decimal. So what we want to know is what the possible error is in volume. Make sense? Kind of, sort of?
Is there any chance you can move the camera over? I can't see.
Yeah, I was wondering about that.
Sorry.
Not a problem.
That's good. Thank you.
Not a problem. All right, so what we want to know is how far off our measurements could be for volume. When we throw in 0.7, we find out that the volume as we've measured is about 1.4368 inches cubed. How accurate is that? That's what our question is. So what we're going to do is we're going to find dV as a differential and then apply that to our measurement here. So dV is equal to 4 pi r squared dr that means the change in volume about this point is going to be about whatever this number comes out to be. I'm going to be honest, I have no wild idea. But this is going to be the rough change, the rough estimate of change in our radius or in our volume. So having said that, you'll notice a difference in the way I wrote things on the board and the way they did. They're using a plus and minus. We're going to apply that in just a second. But what it comes out to be, the solution here, is that the change in volume is about 0.0616 inches cubed. Now, the reason why they have this plus or minus is that they already went ahead and declared that the change in radius is plus or minus 0.01. Okay, you can do that. I personally prefer to apply the plus or minus down here at the end, now that we know what the variability is in our measurement. When we go back to introduce it into our original measurement, we can use that plus or minus then. Make sense what I mean? So once we have this possible error, we're just going to add and subtract that into our original measurement. And that'll tell us what the range of possible volumes is for our sphere. Does this make sense to everyone? I'm assuming from the silence that's a yes.
For the answer, is that zero? Is that like supposed to be a 0.006 or is it a 0 then a 0.06?
It is 0.0616.
Okay. Okay, thank you. Sorry, I couldn't quite see the decimal.
Not a problem. And there's a decimal up here too. And a decimal over here. So what we're doing here is we're saying, all right, we know a thing. We know our measured volume based on our measured radius. But our radius, there's an error associated with it. Given that there's an error associated with it, what's the error that's going to be associated with our volume? And that's what we've just found, is how to calculate that. So now we know that the volume at 0.7 inches is going to be equal to 1.4368 plus or minus 0.0616 inches cubed. Having said that, we can also measure this or report this in terms of percent error, in which case we just say, what is the dV value divided by the measured volume? And in our particular case, it would come out to be 4.29%. Having said that, that is all I had on chapter 3 or on section 3.8. Getting now into 4.1. 4.1 is going to be all about exponential functions. Now, an exponential function is any number 0 or greater and not 1 taken to some power x. Having said that, there are a couple of rules of exponents that we should recall. For those of y'all at home, these are all the slides immediately after starting 4.1. As a couple examples of how these properties apply, let's notice here, pull out this 1/2 power and apply it to both of them after the multiplication of 2 and 3, right? So this should come out to be 6 to the 1/2 power. This, we can do one of two different ways. We can apply that negative through and get that this is 3 squared. Or we can say 1 to the negative 2nd power over 3 to the negative 2nd power. And work it that way. So just as a couple examples of these rules and properties, y'all should have seen this in algebra class in the past. So I'm really just kind of glossing over this. It should be a review. Having said that, a common question is, when are we going to use any of this? When does this stuff show up? One example of where it shows up is working with carbon dating. Carbon dating, for those who aren't familiar with it, is the practice of using the ratios of carbon-12 to carbon-14 molecules and using those ratios to determine the age of a thing, because any living object will have a certain amount of carbon-14 in it. I believe it's carbon-14. Yeah, because carbon is the 14th. 6. Carbon-12. Yeah, it should be carbon-14 and carbon-12. Anyhow, doesn't matter the details of that. What matters is, where does it show up? One example is carbon dating. And all this question is asking us to do is plug in 10,000, 20,000, 25,000, into our equation for t and simplify, basically. Just run through the arithmetic. Nothing groundbreaking here. So we did the arithmetic, and out comes our solutions, right? Like I said, nothing revelatory. Having said that, we should note that the graphs of exponents of exponential functions come in two different flavors. If a is between 0 and 1, and a is greater than 1. In the case that a is between 0 and 1, we have exponential decay. And it decays asymptotically to 0. So as we approach infinity, our function will approach 0. And then in the case when a is greater than 1, we have exponential growth, which is basically the same graph, just flipped, reflected across the y-axis. In both cases, however, for simple exponential functions, we're going to pass through the point 0, 1. And that's because anything raised to the 0th power is 1. That just as a reiteration of this, we have 1/2 raised to a power, exponential decay, 2 raised to a power, exponential growth, 3 raised to a power, exponential growth. So just some details about the two different types of graphs that you might expect. Notice in this case, we could rewrite this as 1 over a to the negative x power 2, right? Like we could rewrite these in different forms to get equivalent statements. So here, if this was a to the negative x power, we find ourselves in this case, right? So this is just all what they're trying to explain here. Having said that, another observation to make, whenever we're graphing these things, it helps to know how we can break these down into more simple exponential functions. What I mean is, in this particular example, we could say there's a function. Let me erase some of this. We could say there's a function g of x equal to 1 over 3 to the x, right? This thing would be equivalent to 3 to the negative x. Its graph would look something like this. So then the graph of f of x equal to g of x minus 1 is going to be this graph just shifted down 1 unit, right? Nothing again revelatory here. All we're doing is shifting this down by 1 unit. Again, more review from algebra. If anybody needs though, I do have all this included in my algebra review notes. So if y'all need to go back to Blackboard and check out those review notes, please do. Having said that, I can't really get into 4.2. Not in 3 minutes, 2 minutes. So I will let y'all go. If y'all have any questions, I'll stick around.